Hi, I'm Jonathan Godfrey,
Hello, I'm Arasu.
Hi, I'm Mason Matich.
Hello, I'm Clair.
and this is Arnold, our cube satellite, and we are Team Gamma.
So this is our final CubeSat design. It consists of a Raspberry Pi, a battery, a solar panel. That blue circuit board you see in the bottom is our IMU, which is how we measure our satellite location, as well as a camera, which acts as our payload. The challenge with CubeSats is that you only have a 10 by 10 by 10 centimeter volume to put everything inside. So our main issue in designing was how do we fit the battery and the solar panel in with everything that you see at the bottom. So the solution was to put the battery and solar panel on the top panel and then connect the power from the battery to the Raspberry Pi at the bottom, which then would go on to power the IMU and the camera. This is our concept of operations, or ConOps. It's divided into three different sections: launch, orbit, and ground operation. And the first two will take place on our CubeSat. So in our quote-unquote launch phase, our satellite is powered on, our IMU is calibrated, and it will connect to our ground station. In our quote-unquote orbit phase, or when we're moving the orbiter around in the circle, detection of guano happens, and it will also take photos based on detection of guano. And all that will be compressed into a folder, and that data then gets sent to our ground station and enters our ground operation phase, where our photos are received and unzipped, and then image processing occurs. And then our final results are then published to GitHub. Our CubeSat software architecture is divided into a boot and normal operation mode, represented by white and green respectively. So during boot, our satellite is plugged in and runs our flight software, which will try to connect to our ground station. If it cannot connect to our ground station within 10 seconds, it will enter a fail state and reboot up to 3 times. Once it does receive a ground station message, it will clear the boot log, so the next time the satellite is plugged in, it will have 0 recorded reboots. It will calibrate our IMU, and it will clear our data folder. This then takes us into normal operation. So what we were doing is we were leveraging something called the multiprocessing that allows us to run Python scripts in parallel. What this allows us to do is after our first photo taken script runs, it allows us to spawn 2 new programs. A send program that sends our data to our ground station, and then another pass program or photo taken program. So that allows us to always be taking photos and always be sending data down to our ground station. So we don't have to dedicate any orbits just to data transfer. The white lines connect all of our photo taken passes to our photo script, which creates a pass folder and then runs a detection script, which checks to see if there's guano in a camera stream. And if there is, it'll take a photo. And that will loop up until one complete rotation, or 360 degrees, after which point it will exit and spawn the new processes. The black arrows connect us to our send script, which compresses our photos and put them in a zip folder, along with some telemetry data, which includes the time the folder was created, how many photos should be in it, as well as CPU, RAM, and disk use. And this will be sent to the ground station. But if that fails, the zip folder will be sent to a dump folder for further use. So after send 10, we will clear the sync text, which is how the photo taken script knows what rotation it's on. And then anything that's in the dump folder will be downlinked to the ground station. So any files that previously didn't send will be sent then.
This is a code to demonstrate a roll, pitch, and yaw. We had to calibrate our gyroscope and had to use some pretty awesome combination of math and computer science to overcome the gyro drift. The main drawback to using the gyroscope over the typical magnetometer and accelerometer combination. This really allowed us to trust our bearings and be confident in where our CubeSat was at each moment in the round. This is the code to detect guano in real time. Rather than the conventional method of taking a lot of images and detecting from there, detecting from the live feed saves us computational time and data space in the long run, and has never been the point of failure in any of our remaining tests. This module has been extremely efficient and reliable.
So on actual flight day, there were a lot of failures. What we did was have one person from our team go into the main room and act as the orbiter, plugging in their Raspberry Pi at the right time, and then completing 10 orbits within 10 minutes. They would also have had to set up the guano for the penguin colonies. The 3 teammates at the ground station would be responsible for connecting to the flight satellite, receiving images from the flight satellite, and using those images to determine where the penguin colonies were, how many colonies there were, and the area of each colony in millimeters squared.
This is our ground station software. As you can see at the beginning, we identify the other Raspberry Pi's IP address. We then connect to the Raspberry Pi and begin listening for the next transmission. All in all, when we're finished, we receive 9 of these passes, which will hopefully be showing up any second now. As you can see here, we received the zipped file containing the passes photos, along with some telemetry data explaining that we received 1 photo, the time and date, what rotation we were on, and then some stats about the Raspberry Pi, including CPU usage, RAM usage, and disk use. As you can see, this is what a successful pass looks like. We have 9 passes and a 10th, which is used for redundancy. As you can see, we have approximately 2 photos per guano. This is because our image processing code was running a little bit too fast for the 1 rotation per minute rate. Luckily, this redundancy came in handy because we got more photos to choose from.
The biggest failure of our flight day was that I tried to implement a new feature on it. I was trying to get the satellite to take a picture at the start of every orbit. That way we would know what our offset should be, because our IMU calibrated wherever it was and considered that 0. So we needed to know where the satellite was starting, so we knew how much we needed to offset our degree values. For whatever reason, when I implemented it, it completely bricked the software. It would only take a picture at the start of every orbit, and it wouldn't do anything else. I reverted it back to the last working build of our flight software, and we did some emergency testing with my group to make sure that everyone had the right version of the software. And we went to go test, and it worked on me and Jonathan's satellites, but it did not work on Clair or Ardash's. It's a lesson on why on the last day, you don't try and add any new features, you just stick with the ones you have and make sure those all work.
So one error that occurred on flight day for me personally was that my CubeSat, even though it did connect to the ground station, wasn't able to send photos or telemetry to the ground station. Actually, when I went to go check the SD card to see if it had taken photos at all, I found that it only took a photo at the start of every orbit. We think that this may have happened because my code was outdated, even though I tested it right before my round, or the code was just a little spotty. The reason that all of this was possible was that we worked really well together as a team through planning and writing and communication, and it always felt like we were having a fun time and getting to know each other, even though it could be really stressful at times. Everyone had different strengths, and at the end of the day, we were all really proud of what we were able to accomplish together.